If D is a solid region in space, and it has a density given by a function delta of x, y, z at a point x, y, z, then we saw that the mass of D was given by the integral of this density over D with respect to the volume form, which is dx, dy, dz. And now we've seen a few different ways of calculating these types of integrals. So a closely related concept, which is very important, is the notion of the center of mass. So that's what we'll discuss in this video. So first, we'll discuss the concept of the first moment of D, let's make that real D, of D with respect to a plane P in 3D space is m sub P equals integral over D of, so this dp xyz is the distance from the point xyz to the plane P, and then we multiply that by the density when we're integrating. So we saw in the first unit how to calculate the distance from a point to a plane, but we won't need sort of the general complicated case. So we only need this for the coordinate planes. So if we only care about back to the coordinate planes, let me say R. Okay, so there's 3 coordinate planes corresponding to omitting one of the 3D coordinates. So the moment with respect to the YZ plane is triple integral over dx times the density. The moment with respect to the xz plane is triple integral y delta xyz dv. And the moment with respect to the xy plane is integral over dz delta xy z dv. And again, the mass of D, which we'll just write as m, is the integral where we're not multiplying by anything, we're just taking the density. Okay, so once we have defined the first moments, the center of mass of D is defined to be x yz's, or x bar, y bar, z bar, is m yz over m. So the moment of, so y bar is the moment with respect to the xz plane divided by the mass, and z bar is the moment with respect to the xy plane divided by the mass. So why are we interested in this? Maybe first let's discuss the principle of a lever. So if you have a lever where there's some fulcrum here, we have a big mass, m1, and a smaller mass, m2, and these are distance 1 and distance 2 from the fulcrum. So this is balanced when m1 d1 is equal to m2 d2. So this coordinate we're multiplying, the y or the x or z coordinate that we're multiplying by the density, is a distance, and this quantity is representing a mass. So this is why you would be multiplying a mass times a distance. So in this lever example, your d would really consist of both of these masses together, and then you'd be looking for the distance to this, or I guess you'd be finding the x bar. So this would be the center of mass. So another way of thinking about this, an equivalent way of stating this definition, is so x, y, z are such that, and I guess that was a 2D example. I'll just write that down, formula down in a second. But these are such that integral dx minus x bar delta dv equals 0, integral y minus y bar delta dv equals 0, and the same for z. The point being, now you're calculating the moment with respect to the line, where x is equal to this x bar. And so in the lever setup, as I said, your region would be this entire thing, and so it would be balanced if the integral here is 0. And yes, in general, in physics and engineering, we can often treat D, which might be some weird, funny shaped region, as a point mass. So a single point of mass m concentrated at x bar, y bar, z bar. Okay. So right, I said for 2D regions, we just write those down explicitly. So for 2D regions, m would be integral over d delta xy dA, the moment with respect to the y-axis is integral delta x delta ay dA. The moment with respect to the x-axis, we integral y delta xy dA. And then the center of mass will be x bar is my over m, and y bar is mx over m. So be careful that the subscripts go opposite to the variable that you're integrating with respect to. So x bar will match up with the integral where you're integrating x, but the name for the moment is is m sub y. Okay, so for example, if you had some sort of plate and you were trying to thin plate and you were trying to balance it on a thin column, you should place it, in order to balance it, you should place it right below the center of mass in order for it to be balanced as well as possible. And when the density is constant at 1, so we're not really taking into account the density or mass, really, we're just calculating, it's only dependent on the shape. We call this the centroid of D. So for a circle or for a square or something, it's clear what the center should be. This gives a good definition in general for the center of any plane shape. Okay, so I'll do examples of these in separate videos. The next concept I want to discuss are a different kind of moment. So the first kinds of moments we just discussed are sometimes called first moments. And now we'll talk about second moments, or moments of inertia. So this is relevant to if we've got some sort of shaft and we've got our object is some object rotating. So maybe we've got like a vase or something on a lathe. And it's rotating around this shaft with so this thing rotating has some density. But it's also rotating around this. So we want to know how much kinetic energy, is stored here. So let's assume that this is moving at constant angular velocity omega, which is d theta by dt. So recall, in general, kinetic energy is given by Ek is 1/2 mv squared, where v is speed. So if v were velocity, we would write like bars v around this. Okay, so if we've got angular velocity of omega, and let's say this is an object is distance r away from the axis of rotation, then v will be r times omega. So r times d theta by dt, or r times omega. So our expression for kinetic energy becomes 1/2 m r squared omega squared. So now if d is, that was just for sort of one point rotating around. So if now d is some region like this, so d, a region of where it's possibly varying density. So if this was a vase, you can imagine it made of differing thickness of clay and varying distance to the axis of rotation. As in our diagram, then the kinetic energy stored in this will be a continuous version of this formula, will be Ek. Now we'll integrate over d 1/2 r squared, but the m will get replaced by delta xy, so the density, and then this omega squared, and all with respect to dA, where again now r, I guess I should say r xy is the distance to the axis of rotation, and now that could vary. But omega, this is a constant, so we could pull that out. So really the most interesting thing, and the most important thing, is this quantity. So this is what we call not that entire integral, but we'll also pull out the 1/2. So the integral over d of r squared, maybe it's better to write r of xy squared delta xy. This is called the inertia or the the moment of inertia, or the second moment of d around the axis of rotation. So now that lets us rewrite this formula. So the kinetic energy of d will then be 1/2 I omega squared, whereas when we were just discussing a single sort of point rotating at constant, a single point with constant mass, we said it was going to be 1/2 omega squared mr squared. So this I is acting as a replacement for this mr squared. But once we have that, we can treat like the rest of the equation looks the same. So in general, we say a moment. So this is called a moment because, or the second moment, because of the power 2 here. So in general, the kth moment with respect to like an axis, or in 3 dimensions with respect to a plane, is the distance to the power of k, and then integrating the density. Okay, so now in the remaining videos, I'll work through some examples.